Okay, so we'll get started. Good morning. Welcome to Center for Research and Computer Vision, CRC for short, seminar series, and this is our inaugural talk today. And CRCV was announced last summer to expand our activities in computer vision. We're going to hire 3 more faculty, tenure track, and several research professors and postdocs and graduate students and so on. And we also will continue the activities for undergraduate students. We have research for experience in computer vision announcement there. And this is the press release from UCF about the center. And so we have quite a few seminars scheduled this month and next month, and that list is also given there if you are interested. So today's speaker is Dr. Elli Angelopoulou. Is that right?
Good enough. Yes. Yes.
From University of Erlangen, Nuremberg in Germany. She got her PhD from Johns Hopkins in '97, and then she was a postdoc at UPenn in Grasp Lab, and then worked in Stevens Institute as assistant professor, and she has been in Germany for the last 6 years. So she has done interesting work in computer vision, in particular medical imaging, 3D reconstruction, and several other areas. So she's going to talk about recent work she has been doing.
Thank you. It's my pleasure to be here. And I'll talk about some of the work that we've done on color. If at any point you have any questions, please feel free to interrupt. I'll be more than happy to answer your questions. So most of the talk today will have to do with Illuminat-Color. Why do we care about Illuminat-Color? Well, if you see at this example here, I can have exactly the same object in a scene taken under different illumination conditions, and it can look quite differently. And I haven't changed much here. We have the same lemon, but if you can see here, if it's illuminated by a regular incandescent light bulb, and I only see part of the lemon, I may even think that's an orange. And the point is that if I have exactly the same scene, but illuminated by different color, and these different illuminants don't vary that much, the appearance of the scene can change, and that can have an impact, a negative impact, on a number of image analysis algorithms, including object detection, tracking, object localization. So there are a number of techniques out there right now that try to address this problem and create either invariant representations invariant to the color of the illuminant or canonical representations. We will talk about how we can extract information about the Illuminat-Color, but more than anything, we will see, this is working too, excellent. We will actually see how we will not deal with the Illuminat-Color as a hindrance, but as an extra clue that can help us determine whether an image has been tampered with or not. So I will divide the talk in 2 sections. The first section is going to be a little bit more theoretical, and will have to do with how do we go ahead and estimate the Illuminat-Color from a scene, and we'll introduce a framework that is based on conditional random fields that does that. And then I'll talk about the second part where we say, okay, now I have the Illuminat-Color estimated at different parts of the image. How can I use it to determine a method for verifying the authenticity of an image? So let's start with the first part of the talk. What is the challenge in Illuminat-Color estimation? If I look at the color at a pixel, I can see that it is really affected. It's really created by 3 contributing factors. I have the geometry of the scene, and means I have the geometry of the object that affects it, where my light source is positioned, and where the camera is positioned. Of course, I have the material of the scene that can affect appearance. A furry sphere will look very different from a plastic sphere. And then I have the color of the incident light, which is what I had motivated a couple of slides ago. It's a complicated system. It's an under-constraint system. I have multiple factors, and I have only one image that I have to infer this information from. So, typical thing, let's make some simplifying assumptions just to be able to tackle this problem. And the typical simplifying assumption is that in the scene I have just one single dominant illuminant, and that is an example such scene that you see up there. That's all nice and reasonable. The problem is that if we look at a scene, even in this room, I don't have one single dominant illuminant. I have the overhead lights. If I'm close to the door, I have light coming from the outside. I have the projector itself that can act as a light source. And that's such an example scene can be seen here at the bottom. So the new trend, and what really the researchers have been focusing in the last year or two, is how can we tell what the illuminant color is when I have multiple light sources? And that's what is our focus as well. When I have multiple light sources, what is critical is the spatial distribution of the lights. So I have different light sources, as you see here, the overhead lights, and I want to know the light that is falling on this part of the scene versus the light that is falling on that part of the scene. So we need to have a methodology, a framework that considers the spatial distribution of the multiple illuminants. And that's where the use of conditional random fields comes into place. So let's look how we set up the conditional random field. I'll go into more details in the next slides. Given an image, I segment it into different patches. Use your favorite segmentation method, use a grid. It doesn't really matter. All I want is to have local regions that I examine. For each region, I have a node that is associated with that region. Then I have at each node, I store not only the actual pixel values, the RGB values in that part of the region, but also I associate with it a label. A label that has to do with what I believe is the illuminant color that is incident on that little patch. And the critical part, and what a graph allows me to do, is to connect neighboring patches. So I compute the illuminant color in isolation, but I exchange information with neighboring labels. If the two patches are not neighboring, then I don't have a connection between them. And it is exactly...
So
yes.
Are you going to assume that you know the location of the light source, or that's not?
No, that is not part of the aspect of the framework. All we need to know is, like, I don't care where the light source is coming from, what is the color that is falling there? Yeah, good question. Okay, so I estimate the illuminant per patch, but then I use the overall framework to find a consistent labeling over the entire scene. And I use the conditional random fields to find the labeling which has the maximum probability of occurring. So now that you have an overview, let's go into the details of how we set up the conditional random field. So I have a graph with a set of vertices and a set of edges. For each vertex, and that's the important thing here, I have a random variable, x, that is the color of the illuminant. Now, I have the scene, and let's say that it seems that I have three dominant illuminants, three different types of illuminants. I have the fluorescent light, let's say I have the projector, okay, two in this scene. So I have two dominant illuminants, but so with different colors, and I want to be able to assign in each label at the end which dominant illuminant is the one that is illuminating this patch. So this is what the value here, x, is. The RGB value of the dominant illuminant at that patch. Then I have also, of course, since I have a conditional random field, and all that information is based on the actual data that I have. So what you see here as phi sub j is the set of RGB values that I have in that patch, image patch. Oh gosh, my equations are all messed up. Okay, but it still should be readable. Okay, so it is what it is. So what is my goal? I have my labels at each node. I have the data, the observations at each node. what I want to do then is find the labels, the set of labels over all the patches that has the highest probability of occurring, the maximum a posteriori probability. This is equivalent to finding that labeling, that set of labels that minimizes the Gibbs energy on the conditional random field. So I'm talking about energy. What is this energy then that I want to minimize? So, given that I have these observations F, I want to find those labels X over the entire set of nodes, over the entire set of patches that minimizes this potential energy here. And I have two components in this energy. We'll spend the next 5 to 7 minutes describing these components. The first component has to do with what we call the Unary potential, and it is the cost of, given the data in this particular patch, what is the cost of assigning, what is the consistency cost between the data that I have in the image and the label that I have assigned in this patch? Is the data supporting the label that I have assigned in this node? The second part of my energy functional is the pairwise potential, where it says, okay, I have assigned, looking in isolation this patch, I came up with this label. I looked in isolation this patch and I assigned that label. But what is the congruence between these two labels? This is what we sometimes refer to as the discontinuity cost. Sometimes, and we will go through that, we expect these two labels to be similar because they're neighboring, and sometimes it's okay to be dissimilar. So what we will discuss then for the next few slides is what is our Unary potential, which is the cost of assigning a label to the observations, and the pairwise potential. It is very common in image processing to use just pairwise click. Very important, and maybe actually this will help you a little bit understand how we think about color and how we treat these color values. In all these, in the graph, we will end up comparing different color values, either between illuminants or between the values that I have in a patch and the Illuminant estimate. How do I compare this triplet of values? The typical way that we compare color values in color constancy in the field of Illuminant estimation is we treat each color pixel as a three-dimensional vector. And then when I want to compare one RGB vector with another RGB vector, we visualize them as unit length vectors, and we look at the angle between them. So this is the typical similarity measure in the color community. We just look at the angle between the two of them. In the field of Markov random fields, it's very common to have a measure of distance which is between 0 and 1. So in that sense, one doesn't need to go into the angle itself, can only look into the result of the inner product. What is very important in having good results in a Markov field is to have a distance function that is robust to outliers and noise. So it's very common that we take this distance function and we use it as an argument in an exponential function. And this is exactly what we have presented here. This is actually the distance function that we use in our CRF. It's based on the angle between the two color vectors, but we have this as an argument in an exponential function, and sigma is just a factor that controls how sharp we want the response to be to differences in colors. So now we know how we measure distances, and the next thing is that, good, I have been talking about, given a set of values, color values at different pixel locations, to extract the illuminant color. And there are existing methods there, as we have said before, but most of them assume that I have one single illuminant. But I can assume that I have one single illuminant in each patch. My patches are small enough. So I can take these well-established methods and apply them locally. And one of the methods, very simple method that is widely used, it has its flaws, but it's a very simple method, is what we call the gray world assumption. And here the assumption is that if you look at a scene, or in our case a small patch, it is expected that on average the scene is going to be gray. So if I compute the average value on the patch, then whatever deviation I have from these values in the patch, the color values in the patch, whatever deviation I have is the color of the illuminant. If my patch is orange juice, it is because my illuminant is orange. And that's what the gray world assumption does. And this is the typical equation that we have for estimating the illuminant at a patch given the set of RGB values in that patch. Of course, we know that this gray world assumption has its limitations. So the very popular and more robust method is the gray edge method, which extends the concept of this grayness to derivatives. And the basic assumption is that the average color difference in a patch is gray. And it's interesting because although typically we say in computer vision and image analysis methods the differentiation introduces noise, when it comes to color constancy, it actually results in a methodology that is more robust to noise. And the method is general enough where we can have a higher order derivatives because they approximate the way that we believe that human eye now does this cancelling of effects, and also there is a pre-smoothing applied. So before we do this gray edge computation, we smooth our image with a Gaussian filter. And one can see the gray world as being a special case of gray edge. So these are two typical techniques that go into the field under the term of statistical based.
So in
yes.
this derivative thing, so
yes.
it gives you how much is a change?
Yeah, it's a gradient, the usual gradient computation,
so
yes.
So that gives you the idea of the color?
Right. So again, it believes that if I was summing all the gradients in a patch, they should be gray. And if all the gradients are the sum of the gradients, the average gradient value. Now I treat the gradient as a color gradient, is not gray, then whatever the deviation is the color of the incident illuminant.
Constant, then you get the zero gradient?
If it is a constant, if it's gray, then we assume we have the white light. Yeah. And it's very interesting that in many methods for illuminating the color of the estimating the color of the illuminant, we assume that we have we don't look so much at the intensity of the light, but just the normalized color. So if I have a bright white versus a darker, more grayish light, dimmer white light, it would be the same chromaticity.
So the gradient is a vector. So
yes.
You assume that the magnitude of that vector is?
Good point. We normalize all these vectors. So we have their unit length. So given that I have statistics, these methods are called statistics-based methods. So I could have in my CRF estimate the illuminant incident in a patch using just the these methods, and then I look at what my data, my observations give me as the incident illuminant, what I have so far, and we'll see that in a minute. So you can start by saying that I'll iteratively solve this problem, and I start by assuming that everything is illuminated by white light. So my first label is a white light. We'll see how we do it in a minute. So I compare the difference between what my data tells me that the illuminant should be and what the label is currently at that node. and I use that as my cost, my Unary potential. And what we have here as W is a weight function that corrects for the different sizes of the patches.
Excuse me. So
Yes.
The difference between I and X, here I is the illuminant, which is the...
Right. I look at the values at my patch,
Yeah.
and based on the RGB values in that patch, I estimate an illuminant.
Right.
And I have a set of two illuminant. Let's say I have found that over here it's, let's say, a reddish light. It's an RGB triplet.
Okay.
And then I have started, let's say, with this scene with two dominant illuminants, one that captures this fluorescent light, which is more or less white, and then one from the projector, which is a little bit more bluish.
Okay.
And then I measure the difference between, let's say, if I had a reddish light, what my patch tells me that the incident light is, and what my dominant illuminant is. That should become a little bit more clear in a few slides when I show the whole algorithm. Yeah. Other questions?
Can you explain a little
Yes.
bit more about the statistics? I don't see the statistics.
Right. So
What is probabilistic about this?
Right. And that is not my term, and I feel uncomfortable with it. But the color community, for some reason, has labeled these as statistics-based method. There is no statistics about that. I absolutely agree with that. Pardon me?
You call it a random field.
Oh, the random field is not in the estimation. Here is on the graph itself. The labels X are considered a random variable, are treated as random variables. So what I will end up estimating with these energy is the probability of, given the data that I have in my image, what is the probability that the random variable of the illuminant will have this particular value. That's where the probability comes. The real probability is only on the conditional random field itself, not at the local estimates. And I agree with you, statistics-based Unary potential is a misnomer. There is nothing statistical either in the gray world or in the gray edge. But if the community calls it statistics-based, I can only give it's not statistics, but that's what they call it.
Can attend computer vision conference.
Maybe you'll be happier with a physics-based estimation. Because that, again, I cannot go into greater details. Here we have, as opposed to the so-called statistics-based estimators, we do have methods for extracting the illuminant color information using the physics, the optics, the physics of interaction of light between light, material, geometry. I could talk about that for at least half an hour, but I only have 1 hour to talk about the whole research. So, the key assumption here, because we have an assumption here as well, that the color of the specular highlights is the same as the color of the illuminant. We have disagreed with that. We have a publication on that as well. But at this point, we just go with what 80% of the community believes, which is if I look at this specular highlight, whatever color I have here is the color of the illuminant. And a group of researchers said, I can analyze and easily find what the color of the specularity is if I visualize, if I map all my RGB triplets now down to a two-dimensional space. And I have for each RGB triplet, which is what you see here, is the kth pixel in my patch, is going to be a point in the scatter plot in the inverse intensity chromaticity space. The horizontal axis is just the sum of the RGB components, and the vertical axis is a normalized color, what we call a chromaticity. I have one 2D plot per color channel. So I have one for red, one for green, one for blue. So I get 3 IIC inverse intensity chromaticity plots. What is important and what I want you to notice here is that all the diffuse, the matte pixels end up being horizontal, and the pixels that have a specular component are at a non-horizontal orientation. What the original researchers showed is that if I look at this specular component, it will intercept my vertical axis at the chroma of the light source. So I don't have to analytically solve the equation. For every pixel, RGB pixel in my patch, I take for the red channel, and I think I have, oh sorry, the green channel, for example, in this case, I look at the green channel only and see where this pixel lies in this two-dimensional space. I take a second pixel in my patch, see where it lies in this space, and then I just analyze the geometry of this scatter plot. For each patch here that I get, in this example for the apple, I have a different collection of pixels in my image. All the specular ones, I can easily fit a line and find the intercept. And that's the way of getting an estimate of the incident illuminant using this inverse intensity chromaticity space. So how do we do it? Given a patch in my image, I take a grid of cells, smaller cells within it. And each of these smaller cells will result in such an area in the scatter plot which will vote for an illuminant estimate. I create a histogram of all the estimates of the local cells created for me, and the estimate that gets computed more often ends up being the illuminant estimate for that patch. This is more believable because if we actually look at the math and the physics behind it, there is a logic and there is science behind this method, as opposed to the gray world. So I could use then a physics-based method for my Unary potential, and it's more or less the same equation like we saw before, the angle between the estimate and what I think is the dominant illuminant there, and we have a weight here which is associated with a degree of specularity. In the current implementation we have it as a binary weight. If it's mostly specular, it has a weight 1. If it's mostly diffuse, we cannot use this method, so we ignore it. Then I can combine my my statistics-based methodologies and my physics-based methodologies, and then have a Unary potential that combines multiple estimates to increase the robustness. The framework is general. So the only thing then that is missing from our CRF is the pairwise potential, where I compare what the label is in one patch with the label in a neighboring patch, and see if the labels that I have there are in agreement with what the data tells me. And that's what happens with CRFs. CRFs, as opposed to Markov random fields, are very closely tied with the observations. So what I have here are the observations at two neighboring patches and the labels at two neighboring patches. And it's typical in Markov random fields to have this, what we call, or what is termed by the original work as a well function. We want this, think of it as a discontinuity cost. If my labels are diverse and these are at neighboring pixels, I wouldn't expect neighboring pixels to have very separate, distinct illuminants. However, it could be the case that I have a foreground illuminated by a flashlight and a background which is kind of right in the neighboring patch which has a more incandescent light. So there are cases where I could allow discontinuities in illuminance, and that is what this function h does here, which we call it, you can think of it as being the depth of the function, and here it is based on some prior work which shows that if we look at the length of the boundaries between two pixels, the longer the length, so we can use the length of the boundary as a way of discriminating between edges that are caused by illuminant changes versus edges that are caused by materials. And this is the function that we have right now in the implementation. So How have we now summarized and set up our CRF? Here's where the statistics are. I want to find the labeling. This is the set of labels over all the different patches that maximizes the a posteriori probability, has the highest probability of occurring. And one way of doing that, or this is equivalent to minimizing the Gibbs energy, which is in our case given by the sum of these unary potentials and the pairwise potentials. And we have explained in the last few slides what our unary and pairwise potential is. It's just a summary of what we have done so far. So how do I end up using now this CRF? Hopefully the last few questions are now answered. I divide my image into patches. This is K here is supposed to be ... So I have n patches, and I run my local Illuminant estimator. Pick one. We'll see how we evaluated it. So I get a color estimate per patch. If I run that, every patch has slightly different illuminants, so I can end up getting 200 different illuminants. But in the scene, really, I have a limited number of dominant illuminants. So what we do is we cluster. We do just a k-means clustering, and we come up with 2, 3, 4. We decide what k is. In our implementation, we use 2 because the data, the ground truth data that we had in our database had 2 dominant lights. So I come up with the 2 clusters, and I assign, which was the mystery in the whole presentation, at each patch I assigned that dominant illuminant which is closer to the cluster. And then I go ahead and use graph cuts as an established technique for estimating, for solving the CRF. Publicly available code. Very nice. Once we have a label then, so at the end of the graph cuts, I have a more accurate set of labels. I can even have, the framework is general enough to introduce new labels if we choose to. And then I have a dominant label assigned to each pixel. I can even generate an Illuminant map. We'll see that in the second half of the talk. That tells me what I have each pixel colored based on the illuminant that is illuminating the scene. One could smooth the Illuminant map, which is interesting in white balancing.
Excuse me.
Yes.
Would you please explain again
Yes.
how you computed the pairwise one?
Yes. So I have 2 functions that make my pairwise potential. This is just simply the difference between the 2 neighbors, right? The same angle. And I want to look at it in terms of the have a 0-1 function. So we could have, this is a, I don't want to say that. So a very wide version, or like think of it as, in the most extreme case, if I want to put it that way, this can be a unit impulse function, where if they are diverse, I have discontinuity cost. I have a 0 if they are the same, right? So and then I have the cosine to the power of eta to control this sharpness, and I want it, that's why we call it a well, it's kind of an inverse Gaussian. Yeah, as I said, I want to stay away from the impulse function. So I could stop it here. In most MRFs, we just have this as a cost function, just that. The issue here is that when we have edges in the image, or if we look at discontinuity at labels, it could be that sometimes indeed between adjacent pixels I expect to have the same label because they're the same material. It's the kind of, like, let's say, this part of the face versus that part of the face. And sometimes it could be that I really allow, and it is okay to have different labels. So I don't have an example here.
Those localities are where you expect to see the boundaries for the
Exactly. So that's one case. Exactly, and that's what we're trying to do here. When I talk about boundary, maybe that was not clear. At each pixel, I look at the boundary. And Lovichenko, I think, I forgot the names. There was a paper published a couple of years ago where they said that if you look at an image that has been segmented and you look at the length of the boundary between adjacent segments, if you have long boundaries, then they tend to be object boundaries. So they actually have three properties: curvedness, closedness, and how oscillating they are. So based on that idea, we have said, okay, then shorter boundaries, it means that I have longer boundaries, it means that I'm jumping objects. So it's okay to have a different illuminant since I'm dealing with different objects. Okay, so let's move then. Are there any questions about the methodology? So let's look at the results. We have the database. We had existing databases, but they were insufficient. One was just synthetic. The other one had badly labeled ground truth data, which we couldn't really trust. And then we ended up creating our own data, 58 laboratory images, 20 more real world, kind of like we went into the kitchen, took pictures there, and so on. The nice thing about our data here, and really the value of it is, and that in order to create, we wanted to have per pixel truly as closely as possible the amount of contribution of the different light sources. So in the scenes we have two different light sources, and we took per scene 3 images. One with both light sources on, one with only one light source, one with the other light source. Taking advantage of the additive nature of images, we end up computing what is the contribution of each light source. This is just color-coded. Blue is the left light source, red is the light source. So we know how much each light source is contributing, and again we can tell also the in-between lights that we have. We compared our methodology with the techniques that believe that there is a single dominant illuminant, and of course we outperform them. This is the right column is us. You can see in real world images our impact was much more significant. What you see here is again the typical error metric. We know what the illuminant should be, and we see what the illuminant is at each patch, and we compute the angle between them. We take the average over each image and then the median over the databases. The reason we went through average and median is again to try to stick with the metrics that the community uses. And what we have here in the middle column is the most closely related work, which also tries to do multiple illuminants. And just to be on the safe side, we also tested it on the database of this closely related work, although it has this faulty ground truth, and we outperformed them. Interestingly enough, the statistics-based methods work quite well, and that's why they have prevailed. And although it's like, why should the average color difference in the scene be gray? It works. So yeah, it's kind of more the engineering science part. It's like, if it works, we're going to use it. And just to show why we need multiple illuminants, when you have white balancing is a built-in feature in many cameras where we want to neutralize the color in the image and show it as if it was taken by white light. This is the original image. This is if we had white balanced the picture using the ground truth data, and these are 3 methods. This is our method on the right, and the competitors, and we want to believe that we are the best. The numbers show that. The picture looks good. And here we have very tricky scene because it has transparent objects which violate all the physics that we have assumed, the reflectance models that we have assumed, yet the method still works okay. And you can see that the gray world ends up giving more pinkish. The average color really doesn't work when we have such cases.
So when the point here is that you take that original image, get up one on the right.
That white balancing is pretty straightforward. We get the original image, we estimate per patch what the illuminant should be, and then we divide by the color of the illuminant, so we get an image as it would be looking if it was illuminated by white scene. It's just a there's no big thing behind here. It's just that we are, as humans, we're used to seeing images, so we like to see images that are kind of white,
No, but
illuminated.
From
Yeah.
the image analysis point of view, once you do all that, you get a better image.
Yes.
And then it could be
Once I have, so one way to think about it is when I have the white image, I can do object recognition there. I can do tracking there.
so that's
Yes, that's why. So the next step often is to just neutralize the color and take it out. But what we will show is how we can actually use that information in image forensics. So we don't want to get rid of that information. We actually want to exploit this information. And technology has improved, advanced a lot. So we can digitally manipulate images and make beautiful pictures. This is a form of art now. Sorry, here. And it's fine. We know it's obvious these images have been manipulated. But what happens when images are presented to us as truth? 150 years of image tampering. The famous Lincoln picture is not Lincoln. And it continues today. So what we had here is just this summer, or was it fall, to make a more dramatic effect in the newspaper. We had this fake picture, but we see it in the news. We expect it to be true. So that is, they took this family and thought it would be a more dramatic effect if they just positioned them in another city altogether, but it's in front of ruins. So everybody's like, oh, poor family. So that then raises the whole issue and the new field of image forensics. Can we trust the images that we see? Can we develop, so the field of image forensics tries to develop methodologies that can attest to the authenticity of an image. Within image forensics, we have the field of blind image forensics. I don't have watermarks in the image. I don't have any security schemes, yet I still want to verify whether the image has been tampered or not. So then we look for inconsistencies in the image. Very common type of forgery is when we have this image splicing. So we take a cut out region from one image and put it in the other. This is an award-winning wildlife picture. And then somebody noticed and said, wait, I know this wolf. It's actually a trained wolf. So they had the wolf jumping obstacles, took a picture of them, and copied them over on this scene. Of course, if you feel a little bit more relief, the award was taken back. And this happens very often. It's a very famous topic, of course, is to splice people. So in this particular application, we'll look into splicing and splicing of people specifically. So you should be able to recognize some of these actors, so it should be obviously that these are fakes, although you can see that some of them are just look quite realistic, I would say. So how do we do it? Well, I should, if the faces are in the same scene and they're next to each other, they should be consistently illuminated. It can't be that I have two faces next to each other and they look inconsistent. But if we look at this scene down here, these people seem to be illuminated from the left, and this person is all in shadow. These we can see easily, but there are finer differences that we cannot pick easily with a naked eye. So this is the idea now. I can estimate the color of the illuminant locally with pretty good accuracy. So what if I look at two faces and the illumination pattern in these two faces and tell if the image has been doctored? And that's exactly the idea that we have here. We assume that in this region that we are examining with the two faces, we have the same dominant illuminant. And then we compare just the skin. So we make things very easy for us because we eliminate other parameters, variants in the image. We compute the local illuminant estimates, and then we do further processing in computing texture and contour information in these images. And then we just run our classifier for pairs of images. So let's look at what we do once we have the illuminant estimate. I have the illuminant estimate, and I create this illuminant map. In the illuminant map, I just color each pixel. So this is the original image, this is the illuminant map. I color each pixel according to the incident illuminant. So here you can see, of course, you can see there's a flaw here. It tells us blue light. It's mainly influenced by the underlying color. So there are imperfections in the Illuminant estimation method. So, and then I analyze the patterns in this Illuminant map. For this method, we use two different approaches, two different techniques for estimating Illuminant maps. One is based on gray edge, and one is based on this physics-based method, which we call here the inverse intensity chromaticity space. So I get, per picture, two Illuminant maps. Let's take a closer look to the Illuminant map. Here I have contrast enhanced the image, but you should be able to see more or less that I have three people here and things in the background. And if I look closely to the Illuminant maps, I observe two properties. One is that I have contours, and we will see more closely into that. Part of the contours is exactly where we have borders of objects, and also within the same material. As I said, I'll talk about it in a minute. And I also have a fine texture pattern. So our idea is like, well, it seems that these are two specific characteristics for Illuminant maps. Let's exploit them. Let's look at the texture. This is the original Illuminant map, and I can see that I have very fine textures because when I look at the interaction between light and material, I cannot expect that at every single pixel I'll get exactly the same value. There are variations between because of non-uniformities in material, non-uniformities in the light source itself, and these are very subtle variations that appear as texture. If I have two different Illuminant colors, I expect that this pattern will change a little bit because my Illuminant has changed. So I expect the texture to be different from Illuminant for different Illuminant colors. So I want a texture descriptor that will pick up on these differences. And the texture descriptor that we chose, and many out there, is the so-called SASSY texture descriptor, because it combines the nice properties of the correlation-based texture descriptors, which can pick up on fine granularities, and at the same time it examines windows at different scales and orientations, so it follows the attribute of the spectral, like the Gabor filters, texture descriptors, which can capture more periodic textures. The key component here, and what I want you to remember from this presentation, is that instead of having exactly the same window and correlating them, which is the typical way of the early on texture descriptors, is that I now have windows of different orientations and shapes. And I compute the autocorrelation between these two differently shapes textures. This is the actual algorithm. For completion is in the presentation. Basically, for each pixel, I look at a variety of different scales, orientations, offsets, and I create per pixel a texture descriptor that gives me the mean and the standard deviation of the autocorrelation.
So this is yours?
No. This is not ours. This is a couple of years ago it was introduced. This is just, we only use it. No, that's. Then we looked at the Illuminant maps again, and we say, but if I look into faces, look, and again, this is a contrast enhanced. I have these contours that I see even in smooth areas. I have contours when I change materials, like around the eyebrows, but even within smooth areas, I get contours because the orientation between the light and the surface normal change. So if I was looking at the actual image, I would get these, what we call them isophot contours, so contours of equal intensity. I have an after effect of that in the object itself. If I change the direction of the illumination, the angles change, so then I have different contours. So if I look at the distribution of edges, of edge orientations, then I get different, I should be getting a different set of curves. Weaker clue, but it's still there. So what I need is a descriptor that captures for me the distribution of edges. And this is what we have now proposed. It's based on the histogram of oriented gradients, and we call it the hog edge descriptor. We have a training set. I only compute the descriptor at points, specific key points, and then kind of like the bag of words, for those that are familiar, I create a code book from these histogram of oriented gradients. Given a new image, I find my key points, I compute my hog descriptor. I'll go through this very briefly. Then, given a hog vector, I map it to the closest code word in my code book, and then the histogram of code word counts in the face becomes my hog descriptor. Key point selection, very straightforward. I run a canny edge detector, and then I select sparsely positioned points there. Oops, sorry. Then the way I compute is the typical histogram of oriented gradients. I look at a cell, compute the histogram of gradients there. Oriented gradients, original version had 9 distinct quantized gradient directions. Then I look at a set of cells around my key point cell, and I concatenate the histogram of all these cells. The last two minor things is I want to focus on faces. I need to localize faces. How do I do that? I could either use a face detector, I could ask the user to click at the eyes, or I could ask the user to click at the corners of the faces. As we will see, the last methodology works better because the user really can be careful on picking a bounding box that only includes skin areas. If we have other materials, it will affect the accuracy. So, I have the texture descriptor, I have the edge descriptor. I have 2 Illuminant maps, one based on gray edge, one based on IIC. So I have 4 combinations of descriptors that I have. And then I'd look at all pairs of faces, and I say, are these 2 faces consistently illuminated or not? So I have a large combination of faces. Each face has a descriptor, and I concatenate, for example, the sassy on gray edge descriptor for one face with the sassy gray edge on the other face. So I compare similar quantities. I use an SVM classifier. I can do 4 separate classifiers giving the 4 different descriptors. And of course we tried a combination, which is the so-called SVM metafusion, where we merge the marginal distances of the SVMs, and we had our own database, own images that we captured, and also images collected from the web, because we wanted to test that our method is generally applicable to a number of images, not just the ones that we collected. And as expected, the combination, the metafusion, outperformed, gave us the best results with 86.3 accuracy in detecting falsified images, followed by sassy on Grey World, and the weakest performer was Hog Edge on IIC. We also compared the different face recognition methods, face detection methods, and as expected, corner clicking gave the best accuracy for 78%. The numbers are somewhat different because our face detection method only detected 60% of the faces in the images. And we also compared it to other methods out there that try to exploit the Illuminant information, and we are significantly outperforming these methods as well. Our method, we also did additional tests. We outperformed human experts. We are really much better in detecting forged images than human experts. We applied a method on other images on the web. We did very well there. We trained on one database, tested on another, across database, did very well. And we also tested how our method deteriorates if there have been other manipulations in the image, if it has been JPEG compressed, if there has been additional contrast enhancement or brightness enhancement. And of course, our performance dropped to, in the worst case, 60%, but it's still better than what the competitors do on clean images. So, to sum it up, I presented a method for Illuminant estimation method, for Illuminant color estimation that is based on conditional random fields and allows us to incorporate multiple techniques, express them as an energy minimization method, and allows us to incorporate spatial information. And we also showed how this information can be used in image forensics. The last thing I want to tell is I give a little bit of credit to my collaborators. This is mostly the work of my doctoral student Christian Ries, and for the image estimation work we collaborated with people in Barcelona, and for the forensics work we collaborate with the forensics experts group in Brazil. Questions?
We have lots of questions, so we'll
Yes.
have little time for more questions.
Yes.
I would be curious to know if you had depth information like from Kinect or something.
Yes.
How would your the pairwise potentials that you calculate?
Exactly. Very, very, very good point. It's exactly the pairwise potential where that would be, because where right now we have this more or less heuristic that we're using the length of the boundary. If we had the depth information, we would the H function that we have would be directly depth discontinuities in the Kinect. And the one thing that we keep on saying is like, if only we had 3D information and then also additional information where the light source direction is. So these are, if we have this information, we would incorporate them exactly the potential function, and we'll also direction could also be in the second part of the talk where we are trying to estimate the distribution of better justify the texture and the contrast there. But very good question. Yes.
If I understood correctly, at the beginning you said that you have different patches in the image. Then you computed the summation of the high order gradient. So, and you mentioned that how you select those patches is not important.
Correct. We tried. Yes.
So I was thinking, for example, a bigger patch or a patch that overlaps two parts of an object can change.
So I was not clear in what it is not important. We want small to medium-sized patches, but what I meant is that we tried different variants. We tried just having a regular grid. We also tried the Felsensalp and Huttenlocher method, and then there is a more recent algorithm by Wechsler, I think it was CVPR last year, which has the Wechsler algorithm is very good at following the borders of the objects. So
trying to avoid to have a patch that contained the border of the object.
Exactly. So, but that then there is no clear winner, because for the physics-based method, we want patches that, if possible, have the same material. For the gray edge method, we want patches that have edges in them. So one segmentation will work better for one method, one will work for the other. If you know that you will be using just gray edge, then I would say use a regular grid. It will give you better results. If you want to use a physics-based method, I would say use the Wechsler. It will not contain the patch will not contain materials from two different things. But at the end, so it doesn't matter, meant more that there is no one perfect, good segmentation, and you want small to medium-sized patches. So, yeah. Yes?
The labeling that you eventually get can be considered as the light source.
Yes.
So if you have two light sources, then this region is getting the light from this and
right.
to its label.
But the problem is, and I guess I didn't let you finish your question. So it's like,
my question was that typically in the real world, every region receives light from all light sources.
So,
if you, for example, considered labels which are not discrete.
Right. So in the actual computation that we have now, and what we have in the ground truth is that there is no way that I'll have a sharp border that says this part of the image is Illuminant 1, this part is Illuminant 2. So our method actually allows to have the in-between contributions. It's like the framework is general, and you can play with that. You can say I have two dominant illuminants, and then I allow a subset of illuminants which are a combination of these illuminants. So we have lots of variants that we have played with that.
It's more of a point spread function than a light source.
Yes, yes. I mean, the most accurate way to do it is to do a point spread function than having
But
this
I mean, these labels,
discrete.
I thought in MRI formulation, each region has to have one label, right?
Correct, exactly. So the formulation allows you to have that, but then you can put constraints on what... There were additional variables that I skipped. So we have the random variable can only take a specific set of Illuminant values. So we have a label set. So these are the allowable labels. We can have 2 of them, which is the extreme case. We could have the 2 extremes and the kind of distribution, the in-between values. So the CRF can allow you, and as we saw in one of the Illuminant things, to have 200 values if we want to in their Illuminant values. So
the light sources might be 3, but you have 20 different values, and these values will correspond to different contributions.
Yeah. So the framework is quite general and allows that. Yes.
Okay, one more question. Then we start. Yeah, go ahead.
This is a rhetorical question.
Okay.
Finding the data set. So you
Yes.
said that your method outperforms humans in
Yes.
recognizing them.
Yes.
Now, in your data set, you need a reference image, 2 reference faces in the same image.
Yes.
So, I mean, and considering you're manually selecting those data sets, you're already wrong, right? I mean, the humans are collecting the data, but they don't.
So so I skipped that. What we had is we had this, the database for 200 images. We actually submitted it, which all had faces, and were submitted to this Amazon Mechanical Turk. And we had those experts. So it wasn't just in general experts say that, but we had 4 different experts running 2 times, I think, in the Amazon Mechanical Turk. So we had, and then how can we judge the experts? So they claim they're experts. So we had them judge the same images that we had in our database, whether they were manipulated or not. And they just saw the images. They didn't see the faces. They didn't know what technique we used. They were actually much better than us in telling which pictures were not manipulated. So they had like a 90.9% accuracy in detecting genuine images, and then they were down to 38% or 40% in detecting.
So this image you show in the previous one, the men and women. So what was it? Fake
this one is this is not a fake. So actually, it's a real one. It's one of the graduate students in Brazil with his girlfriend, by the way.
Oh, you know that.
Yes, I know. Yeah, we were very nice. No, we didn't do that. So, and then on the right side is a... No, this one is an original. It's again, I think it's a doctoral student in Brazil with his girlfriend.
Original.
Yes, this is an original. Yes.
Okay, great.
For those that are curious.